Hello, and welcome back to another episode of Penrose From Scratch. This time, we're going to look at some slightly fancier stuff with layouts, namely something called layout messages, which is kind of a way that you can set up key bindings to modify the way that layouts are working on screen, which is kind of cool. There's also some stuff around kind of higher order things you can do with layouts if you want to kind of be kind of functional about it, where you can kind of wrap them and kind of modify the way they're behaving, which if you're writing your layout yourself, probably don't need to do. That's fine. You just write it to do whatever you want. But if you want to tweak something that someone else has written or something that I'm providing from the built-ins in the Penrose crate, then it's a way that you can kind of modify that behavior without having to kind of completely rewrite the thing yourself. You can kind of transform it. It's a thing called a LayoutTransformer. Yeah, we'll have a look at that. And also just, you're not limited to only using those traits for doing stuff. So the kind of main thing I was going to have a look at once we'd got message handling today was writing a little kind of layout wrapper, I suppose, or like sort of layout combinator, layout holder thing. Don't really have a good name for it, but I've got an idea that's inspired by a really cool video about someone's Xmonad config, which I will link in the description below, because it was one of the inspirations for writing Penrose, was seeing the kind of cool stuff you can do if you have like library code for writing your own window manager. So I'll have a look at that. But yeah, the kind of thing we did last time was this Fibonacci layout, which is quite nice. It just gets more and more ridiculous as stuff sort of zips off down to the bottom there. We can kind of zoom all the way through. But one thing that it doesn't do is what the MainAndStack layout does, which is this kind of growing and shrinking. And that's done using this idea of sending layout messages that we'll talk about. Now, following the last episode, I did get kind of carried away and made some more layouts. So these are also ones that are kind of inspired by things from DWM, where kind of you can kind of do fancy kind of stuff with it. That one's called Tatami, and it's based on a kind of Japanese mat design, I think. It's kind of fun. But that Tatami one, that handles the layout message stuff. So what we're going to do is pinch the way that does it and add it to our Fibonacci one and see how that goes. And then we're going to have a look at wrapping our Fibonacci layout just as a bit of a demonstration of how to kind of modify existing layouts as well. And then we'll have a look at this kind of combinator idea at the end. That's the plan. So first things first, if we want to steal something from something that's already implemented, the best thing to do is go have a look at the code for that thing. This is a link to where you can see the built-in layout messages and transformers. We're going to have a look at those in a sec. But if we search in the docs for Tatami, that's that new layout that I've added. And we can go to source. Now, if you're in your editor and you have Rust Analyzer set up, you can kind of go to definition in there and you can go do that. I tend to like doing this by going through the docs rather than jumping around my editor if it's something that I want to kind of really understand what's going on, because it means I can bounce between the human-facing documentation and source code, and quite often you'll find that if you're jumping, like using go to definition to jump to like a third-party crate that you don't know that much about yet, can sometimes be a little bit disorientating. You don't really know how to find your way around. Whereas like the search bar in DocsRS is really, really helpful. So just as a bit of a demo, we'll do it that way. So if we have a look, the Tatami struct has got two fields, ratio and ratio step. Remember those, we will need to add those to our Fibonacci struct. And then the layout itself is kind of fun. It's just these little kind of pithy little statements that are kind of splitting up the screen depending on the number of clients that we have. I say pithy. It starts off pithy. It's kind of nice. By the end, it gets a bit silly because you've got to split and recombine stuff all over the place to get it to work. But it's kind of fun. It was a good way to spend a morning while I was drinking a cup of coffee. Now, the bit we care about is this handle message. Now, what we're going to do is grab this and drop it into our Fibonacci handle message, and then we'll see what's going on. because I think it's going to be easier to explain over here. So we're doing that to do. We're implementing handling for some messages that we care about. But there's a couple things we're going to need to sort, as you can see by all of the red error marks coming up down the side here. First thing is M. We're not binding M at the moment, so that's fairly simple. Second one is ratio and ratio step, like we said. So if we come up to our struct, we'll add those in. So we've got ratio, that's going to be a float, and that's going to be like a percentage, like between 0 and 1, what percentage of the screen are we giving to the main area? And ratio step is going to be each time we're told to shrink or grow, how much do we change by? So we can pop those in. We've now got different errors because we're not referencing those anywhere. So ratio, that's going to be 0.5. So we're still doing the kind of cut in half behavior we've got in the moment. And the ratio step can be kind of whatever you want. I tend to find that 0.1 works quite nicely for this, just by kind of empirical testing. Like it's a nice kind of jump. But if you want more fine grain or coarse grain, you can change that to whatever you want. And then we need to pass those through when we actually build stuff. So, oops, it would help if I could type. So we've got ratio and ratio step. We'll need the same here. Ratio step, ratio step. Cool. And then that's going to be unhappy because when we make it up here, we need to provide everything. Now, we hit this last time where we had a little bit of an issue with building this stack because we needed this as the sort of boxed trait object stuff, the boxed in layout. And just trying to put in our Fibonacci struct on its own caused a bunch of problems. Just trying to do a box Fibonacci caused a bunch of problems because that's not, Rust doesn't infer that that's a trait object. It knows it's a Fibonacci struct. So it's like, hey, cool, I have a concrete type for you. So we kind of need to do that with a function to kind of force it. This boxed default is something that I've added for the main and stack trait, and I'm tempted to make it part of the layout struct, layout trait, but then that would be one, breaking change, and two, you'd need a way of doing that. Or you'd always need to be able to default the layout, which you might not want to do. So instead, we'll just add it by hand for now. But this is kind of a convention that's quite nice. Box default is going to return a box dim layout. And we're going to use that turbofish again. Box self. No. Oh, no. Oh, sorry, box self. Default, like that, I think. Is that how I do it? I think that's how I do it. Yeah, cool. And then up here, we can change this to boxed default. And then that should be happy. Cool. Oh, we still have an error. What's our error? Ah, cool. And our error here is basically complaining that we need type annotations, and we'll get to this in a sec, because this is kind of dynamic typing in Rust, which is, I won't go into a huge amount of detail for, I'll kind of explain how we're using it here, but you can end up with some odd stuff here. So the problem is our match statement is referencing a struct, one of those messages that we're going to talk about, but we don't have it in scope. So as far as the match statement is concerned, that's just an identifier. So if we go back to our docs.rs and have a look, we've got in built-in layout messages, this is where that expand main and shrink main and all that kind of stuff lives. So we'll import these from there. Built-in layout messages, and we've got two of them that we care about. We've got expand main and shrink main. And if we import those, then we should get rid of our errors. We should be good to talk about stuff. Cool. Okay, so what's going on here? So a message is literally anything. And I really do mean anything. It's defined using a built-in trait for dynamic typing that's called any. So a message is just a wrapper around a box din any. So a trait object, anything. So it's kind of like a void pointer in C, if you've done that kind of stuff before. It's kind of like, cool, I'm pointing at something, I can't tell you anything about it. Now, in C, you can take a void pointer and cast it to whatever you want. In Rust, we can't do that. We have to cast it to a particular type, and we need to know the type we're casting to. So it ends up being a little bit funky, but this is what that kind of message handling stuff, that kind of if-let kind of bit that we're going to look at is doing. We're calling this downcast ref method, and what that's doing is basically you kind of saying, hey, if it's this type, I know how to deal with that. If you can name the type and say, is it a foo, and it is a foo, you'll get that kind of type conversion, and you'll get access to whatever is in that struct. So in terms of how this is working here, we're taking our message, we're calling downcast ref, and if it's an expand main struct, then that will succeed. We'll get some expand main, and then we know what we're doing. We're going to modify our ratio. We're going to add on our ratio step, and we're going to clamp it at 1.0 because we want to be between 0 and 1. And if it's a shrink main, we're going to subtract our ratio step. And again, we're going to clamp it, but this time at 0 because we want to be between 0 and 1. If you had data in there, like there's an inc main message, which we can have a look at. And in that case, you pass it an integer, and you're basically saying how much you want to, how many more clients or less clients you want in the main area. So if you passed an inc main 2, then the main area would have an additional 2 clients in it, and you get access to that integer when you're matching on it, so you can kind of pull that information out. So you won't really see dynamic typing all that much anywhere else in Penrose, if at all. I don't really think. Other than like this, technically under the hood, this is what the state extension stuff is doing as well. When you're saying, hey, give me this state extension, it's kind of the same idea as that. So those are kind of the 2 places I make use of this. But in the message stuff, you basically match on the types that you know how to handle or that you want to handle, and anything else you just ignore and you return none. So before we were ignoring everything and returning none. Now we can just kind of match on that and kind of say, okay, cool. If it's one of the 2 that we know about, then we're good. Now, this isn't everything we need to do, though, because we're updating our ratio and using our ratio step. So the kind of Rust dead code analysis kind of stuff isn't going to kick in for these fields because we are making use of them. But we're only making use of them in the sense that when a message comes through, we modify the value. We're not actually using the value for anything. So we can modify, we can expand and shrink our main ratio as much as we want until we actually make use of it. We're not actually going to change the way the layout works. So if you have a look before, we were always doing stuff at the midpoint. So we had split at mid-width and mid-height. What we're actually going to do now is we're going to say split at width perk, which stands for %. And we're going to do our self.ratio in there. Now, this returns an option, same as like some of the stuff that we've looked at before with the rect kind of struct. Like if that ratio is out of bounds, then you're going to get none, because it's like I can't split at a sort of percentage of 300% or 4 million%, whatever it is you pass through. So we need to do that bounds check, but we're doing our bounds check down here. So we're actually going to do an expect, which is kind of, it's like unwrap, but you get to set a custom message if you've not seen this before. So we want to say self.ratio is inbounds due to logic in self.handle message. Cool. And I'm going to make use of that expect each place we're doing this. You don't have to be as verbose as that. I tend to like, if I'm using expect, I want a very clear message of why I thought that should never explode. Because if we go away and change what happens in handle message now, we've broken that invariant. So we'll be able to panic the window manager from that. And if you do have that, you kind of want a very clear message about what you did wrong. So we'll do the same thing here. This is going to be split at height perk. And that's going to be the same thing of self.ratio. And I keep typing ration. and this will be split at width perk, self-to-ratio, and our expect. Cool. So we've got that in place, and that means that we're now doing our splits based on whatever ratio we have set. Our ratio is going to start at 0.5, and anytime we get a shrink or expand message, we're going to change that. Nice. Okay, so we've not got any errors, I don't think. No. And we are adding our Fibonacci layout. Let's put that first now. Put the tatami one at the end. And that means that when we restart, that should be the active layout, and we can give this a go. Okay, let's give that a try. So if we go over to Penrose From Scratch and we do make build and sudo make install, we should see how we go. Now, I did try running this previously to try and speed things up, and it's not too much of a surprise that running OBS slows down compiling everything, because resources are being used for other stuff, but it really slows it down. Like, I can get like 3 or 4 second recompile time without OBS running, which is obviously a lot faster than this. 3 or 4 seconds is still painfully slow for something where we've not actually changed that much. But that's Rust for you, I suppose. Slow compile times, but very fast run times, and lots of help for when you make bugs. So actually, I'm fine with the trade-off. It just means there's a bit of dead time to fill in these videos. Right. So if we restart, and we should see that if we go back to workspace 4 now, our default layout is Fibonacci now, rather than that tatami one that we had. And if I start creating some windows, I should then be able to expand. Hey, nice. And shrink. Whee. Oh, that's fun. That looks really cool with... Oh, that's very odd. Cool. Okay. So yeah, so that's message handling. We can kind of shrink and expand that stuff as much as we want, which is kind of cool. And then we can close all those terminals, because we don't really need a bunch of terminals, but sure. But yeah, that's it. That's kind of all we need to do, really. We just match on the messages that we care about, and we update our internal state. Kind of it. So that's cool. There's another thing we can do, which is, say we wanted to modify a layout that we hadn't written. So this is where, if we go back to Penrose built-in layout, there's this module called transformers. Now, we won't go through how to write a transformer yourself right now. You most likely don't need to do it. It's kind of, if you're writing your layout from scratch, then you just implement it how you want. This is for like modifying an existing layout to do something different. So if there is an existing layout that you would like to have different behavior, if it's something that could be added as a non-breaking change, like it's a new message type you could send it and you could change it, then let me know, like raise an issue in GitHub and we can have a look at adding that in. If it's something where you want to do something like this, like you want to reflect it horizontally or vertically, or you want to kind of keep a bit of space at the top or around the windows, then this idea of a layout transformer, which is what we're going to look at just now, lets you do that. You basically just put it around or wrap it around a layout, and it kind of does a bit of pre or post processing, depending on how you implement it, to change the way that those windows are positioned from the layout. So we're going to use this reflect horizontal. So that's coming from built-in layout transformers. So we'll go built-in layout transformers, and we'll do reflect horizontal. And then I think we're just going to have a reflected version of Fibonacci. So we'll do reflect horizontal, wrap this. And that's kind of all you need to do, really. Like you grab one of those transformers, you apply it to the layout that you want to modify, and then you run the layout. So let's try that. If we recompile with that, then we should have 2 Fibonacci layouts now. The first one is the one that we've been working with so far. It's going to drill down into the bottom corner this way. And the other one is going to start over here and drill down this way. So we'll give that a go. We'll restart. And whoops, oh, OBS is kind of going infinite there. And if we go here, so we've got our first Fibonacci, that's fine. And now if I change the layout to the next one, it flips to the other side because we're reflecting it. Nice, and that's kind of it. That's all we really need to do. We can then kind of go through. But if you have a look here, it says there, reflected Fibo. So it kind of lets you know you're running that reflected version of your layout. And yeah, that's kind of all it's really doing. It's kind of just taking the positions that came out of the layout that's inside of it and mirror flipping them across the screen. So we can do that. That's cool. What else can we do? Well, to finish off for today, the last thing I thought we could have a look at is doing something that's kind of completely custom. So rather than saying, I'll implement a layout and it will go and lay out my windows and that's my algorithm I'm going to use, or a transformer that's going to wrap an existing layout and tweak the way that that works, I thought we'd have a go at something that is partially inspired by that really cool video that I mentioned, which I'll have a link for. And if we can get this working, I'll kind of get it tidied up and I'll get some kind of example usage of it in place and I'll get it added into the main Penrose crate. Same thing for the Fibonacci layout. I need to get some tests in place for that to make sure it doesn't freak out for arbitrary inputs. But so long as I can make sure that that's sound and isn't doing any kind of unsafe kind of subtraction or division kind of stuff, which would kind of crash, then we should be good to go. Which would be cool. But this one, the idea I've got is for a thing that I'm going to call conditional. And so a conditional is going to be two things, or three things, I suppose. It's going to have a left, which is a boxed-in layout. And it's going to have a right, which, as you can probably guess, is also going to be a boxed-in layout. And then it's going to have, what should we... let's call it should use left. Let's call it that. There might be a better name for this, but we'll see. So should use left is going to be a function pointer, which is going to take the same stuff as the layout method. So it's going to take this. Is that the right way to do it? I think that's the right way to do it. Yeah, there we go. Oh, but I don't need the names for the signature. I probably should have just typed that out. That would have been faster, wouldn't it? I'm just going to return a bool. So that's going to be a function which gets given the arguments we've been provided for layout, and it's going to run that through this function and say, cool, this is what we're laying out. Should we use the left layout or the right layout? You might see where the conditional part's coming in here. And we'll have a left is active. As a bool. And we kind of want to store that result because it's only when we're laying out we know that. And so if we want to change like the layout name, like we saw with the reflected one down below, or when we're handling messages, we need to know who to handle messages to. We need to store that bool. We need to store the result of should use left so that we've got access to it, because we're not going to be able to call it again because we don't have the stack and screen rectangle to work with. So let's just quickly also derive debug for this. I think that should work. I think you've got debug for a function pointer. I think. We'll find out. Is that going to shout at me? No, it's just going to say it's unused. Okay, cool. Right, so there's a couple of things that we probably should implement in terms of like quality of life stuff for setting it up. But for just now, we'll just kind of hard code making one once we've got this working. And that'll be something I'll do off screen. I'll add all the kind of stuff like this, where you've got a default implementation and helpers with docs around making a new one and boxing it and yada yada and all that kind of stuff. But for now, let's just implement layout for this thing. So if we implement layout for conditional, we're going to have name, and we're going to say if left is active, or self.left is active, then we'll return self.left.name. Otherwise, we'll return self.write.name. Okay. fn boxed clone. We need to do box new self. And we need left is going to be self.left.boxed clone. And this is why we're doing these with trait objects, by the way. When I first had to think about this, I thought that maybe I could get away with this being like generic over two layouts, so L1 and L2, and we'd actually hold on to those. But then we'd need to do the boxed cloning stuff here anyway, so we might as well just have them as boxed clones. Or as box trait objects, rather. And actually, I don't even know if I can do it without that, so we'll see. Should use left is just going to be self.should use left, so that should work because it's just a function pointer, so we can copy the function pointer. And left is active is a bool, so that's fine. We can just grab that as well. Cool. So that should work for doing our box clone. For laying out, we'll do the same trick as we did for name. So we'll do if self.left is active, we'll do, oh wait, no. Before we do that, we need to set self.left is active. So this is how we're going to work it out, isn't it? So we're going to say self.left is active is going to be self.should use left SNR. Oh, I've got that paren in the wrong place. That should be here. So if you've got a function pointer on a struct, you can call that function, but you kind of need to wrap it in parens. In this, it looks kind of odd. It almost looks like it's a tuple. But that's how you kind of call a function pointer that you have stored on a struct. So we're going to call our helper method that we've been provided, our function that's, hey, are we laying out left or right? And that we'll cache that so that when we're checking the name, or like we'll see in a sec, when we're handling messages, we know which side's active. But then once we've got that, we can say if left is active, then we'll do self.left.layout SNR. And if it's not, then we'll do self.right.layout SNR. Cool. And then last bit is handling messages. So fn handle message. And we do the same thing. If self.left is active, then the left layout's going to get the message. Self.left.handle message. Cool. Otherwise, we'll do self.right.handle message. Cool. And then things should stop shouting at me. Cool. Other than, I suppose, it'll shout at me that this isn't used? No. Is it not shouting at me about it not being used because I've implemented a trait for it? That feels weird. But sure. Okay. Cool. And then in order to make use of this, then we need to make one of these things. So let's just have a function for making one. Let's say conditional on odd or even. So this is going to be super dumb. This is, let's return a boxed in layout from this. Having your layout changed based on whether there's an odd or an even number of windows, which is what I'm about to try, probably isn't what you want. That'd be daft. But it's just to kind of show off this working, because the idea is you can pretty much put any function you want in here at this point and change your layout. Now, the thing I actually want this for is the screen resolution for my external monitor, which is what you're seeing just now, is way bigger than the internal resolution of my ThinkPad and the ThinkPad screen. So the thing that I saw in this video was something kind of like this. I don't really know actually how that was implemented. I assume it's something like this, but this should work. Where it was based on the screen dimensions. So if the screen dimensions were bigger than a certain kind of cutoff, then it used a layout that kind of made use of that space. kind of like a 3-column layout kind of thing, maybe. And if it was below that cutoff, then it used a more compact layout that kind of meant that your main window still was a decent size. Like it was kind of making sure that your main window was always big enough for you to work with. But if you had the screen real estate, you could put more things around it. Kind of fun, kind of a nice idea. That's not really going to work for demoing just now because I'm only showing you one screen. So yeah, next best thing, let's do something daft like this. Why not? So box, new, conditional. And so we'll say that left is, let's do Fibonacci boxed default. And right is MainAndStack box default. Sure, why not? And then our should use left is going to just be a closure because we can kind of get away with that. If we don't modify anything, that will kind of cast to a function pointer, which is kind of nice. And we just want to say s.len mod2 is 0. That's going to be our condition for if we flip. And left is active is going to start with true. So we're going to start with the Fibonacci layout. Okay. That all looks okay. So up here, let's do conditional on odd or even. Why not? Oh, actually, and how about, just to make this clear on what we're doing, let's tweak this slightly. So that instead of it just being left and right names, let's do a little wrapper around it. So let's do like conditionally that. Why not? Oh no, how did I do that? I did cond that. Yeah, like that. Okay. So we'll say we're conditionally that one so that we can kind of tell which layout we're on. Okay, and then that's our first layout that we have active. So we should be able to reinstall with that in place. And let me just double check. I think that implementation all looks fine. So the name's going to switch based on whether left is active. Box clone is just cloning the things, and we are cloning left and right, so that's fine. We call our function to work out if left is active, and then we lay out left or right. And then if left is active, we pass a message to the left side, otherwise we pass it to the right side. Okay, so that should work, I think. Let's find out. So our layout loaded, as you can see from down here where it says con side. So that's so cond fibo. Oh, and that was con side because it had a window on it. So if we change that, it flips to side. Nice, cool. Fibo, side, fibo, side, fibo, side. Cool. And if we, cool, so we can send our messages, they go through to the right one. And if we delete a window, so let's make the ratio over here. If we delete a window, it jumps back to being the Fibonacci one. And we can change that. But then if we delete a window, it should go back to the other one, but our split point was further over to the left. And we bounce between. Nice. Hey, sweet, cool, that works. Nice, I like that. That's cool. I will tidy that up and add that to the main crate. That's kind of fun. But yeah, that's kind of an example of the kind of fun you can start having with this stuff once you've got a feel for how all this stuff kind of composes together. You can just start writing arbitrary extra stuff and kind of composing things together. So that's fun. So yeah, I'm just really chuffed that worked. That's great. Cool. So next time around, I think what I'm going to do is have a look at the kind of internal data structures for Penrose. So we've been talking a lot about stacks and workspaces and screens, and I may have said stack set or client set at some point. But whenever I talk about like the pure state for Penrose, that's kind of what I'm on about. We'll have a look at what that is and how that works. It uses some fun ways of writing data structures that are a thing called a zipper, which is kind of taken from Xmonad. And when I found out about it, it's a really nice way of doing this kind of stuff because it's way better than what I did in the previous version of Penrose, where the data structure itself encodes what window or what workspace or what screen has focus. It's really nice. So we'll have a look at that next time. And then once we've done that, we should have enough of an understanding that we can start writing some like completely custom functionality, which would be kind of cool. So stay tuned for that. And until next time, happy hacking on your window manager. And I'll see you later. Bye.